Hello, and welcome to this second video of a playlist about the preparation of alkylarenes. This video is about the direct electrophilic alkylation of unsubstituted arenes with alkenes. For large-scale preparations, this is the most preferred strategy because no byproducts are formed, which could deactivate the catalyst or corrode the reactors. When terminal vinyl groups are treated with acids, secondary carbocations are formed. Aromatic electrophilic substitution of hydrogen by such carbocations then yields branched alkylarenes. This chemistry is conducted on a huge scale for the manufacture of detergents. The main side reactions are hydride abstraction from the product by the protonated alkene and the formation of tetralenes or other oxidized products. Isopropylarenes are good hydride donors because the corresponding cation is well stabilized. The oxidation of isopropylarenes is therefore easy. Cumene hydroperoxide, for instance, is obtained from cumene, air, and aqueous sodium carbonate.
Other side reactions are polymerization of the starting alkene, addition of the acid to the alkene, or reaction of the acid with the arene or the product. Acid-catalyzed alkylations of arenes with olefins work best with hydrogen fluoride as catalyst, a volatile acid easy to remove from the product. Aluminum chloride and zeolites can also be used. Less convenient are sulfuric or phosphoric acid. Linear alkylarenes are more difficult to obtain from terminal alkenes. Certain chelates of cobalt, nickel, ruthenium, or rhodium, however, do yield linear alkylarenes when treated with unactivated olefins by the mechanism sketched here. I'll show you some examples later. One potential byproduct are styrenes, formed by a Heck-type mechanism, but this can be prevented by choosing the right catalyst and conditions. Aryl palladium complexes, however, will usually yield styrenes because of the high tendency of alkyl palladium complexes to eliminate a palladium hydride.
The specific examples of this video are organized as shown here. I'll start with the alkylation of arenes by unactivated alkenes, followed by alkylations with dienes and with electron-deficient alkenes. At the end, we'll have a look at some Claisen rearrangements. Within each group of alkenes, I'll start with neutral arenes, followed by phenols and anilines, heteroarenes, and then metallated arenes, including transition metal chelates. This here is the typical result of an acid-catalyzed alkylation of benzene with a terminal olefin. Despite the short reaction time, all possible isomeric carbocations were formed by hydride migration. Because of the high commercial relevance of this chemistry, many different catalysts have been developed for industrial use. For instance, zeolites or other insoluble acids. These can give higher yields of some of the possible isomers. Allyl or homoallylamines are first protonated at nitrogen. The ammonium salts then require stronger acids for a second protonation than simple olefins. The resulting dications are more reactive and can sometimes even alkylate electron-deficient arenes. Here, benzene was alkylated by a homoallylamine with the aid of a large excess of triflic acid. The olefin was protonated so that the new positive charge was furthest away from the ammonium cation. Here is another instance of the alkylation of benzene by a dication. In triflic acid as solvent, an alkyne reacted twice with benzene to a substituted diphenylethane. Alkynes are dehydrated ketones and can act as synthetic equivalents of ketones. Unlike dications, protonated styrenes are stabilized and thus unreactive carbocations and will only alkylate electron-rich arenes. In this example, anisole reacted with a tertiary benzylic carbocation at position 4. With tert-butylbenzene, however, no reaction occurred. Thus, the less reactive a carbocation, the higher its selectivity. Intramolecular Friedel-Crafts alkylations with olefins tend to be more predictable than intermolecular alkylations. Here, a tetrahydrobenzazepine was prepared in high yield by cyclizing an allylamine with aluminum chloride. Even N-allylanilines cyclized when treated with a strong acid. Here, a solution of antimony pentafluoride in hydrogen fluoride was used,
which is about 10 to the power of 16 times more acidic than neat sulfuric acid. Interestingly, no 5-membered, but a 6-membered ring was formed, although 5-ring cyclizations are usually faster. When dications are formed, the two positive charges tend to be separated as far from each other as possible, and allylamines can therefore yield primary carbocations. Under milder conditions, no cyclization, but only the addition of hydrogen fluoride to the olefin occurred. In this related example, a mixture of the cyclized product and the addition product was formed. Here, the arene was more electron-rich than in the previous examples, and cyclization of a homoallyl ether proceeded under milder conditions, with only 5% of ruthenium trichloride and 10% of silver triflate. No alkylation by the solvent, dichloroethane, occurred. I'll show you now some examples of the alkylation of phenols and anilines with unactivated alkenes. In the presence of aluminum salts, phenols and anilines can be alkylated with ethylene and other olefins. These reactions work best with anilines, but under forcing conditions, also phenols can be alkylated this way. Under the conditions given here, the yield of ethyl phenols was low, however. With propene, and at a lower temperature, a fair yield of the anesthetic propofol could be attained. Catalytic rhenium carbonyl enables alkylations at a much lower temperature. With only a slight excess of olefin and 2.5% of rhenium carbonyl, a high yield of monoalkylated phenol resulted after 2 days at 160 degrees Celsius. This is an example of acid-catalyzed alkylation of a resorcinol with a tertiary carbocation. The intermediate, despite being an unreactive neopentyl chloride, cyclized in good yield to a dihydrobenzofuran. When a mixture of aniline, catalytic aluminum analide, and ethylene are heated, excellent yields of 2,6-diethylaniline can be obtained, as shown here. Single alkylation of anilines has been achieved with styrenes and triflic acid. Here, the polymerization of styrene was a potential side reaction, which can be suppressed by diluting the reaction mixture or by dosing styrene slowly. Polymerizations only proceed if a given critical concentration of monomer is exceeded, and dilution is therefore an effective strategy to prevent polymerizations. Some arenes metallated with transition metals react with vinyl groups at the terminal carbon atom, yielding linear alkylarenes. In this example, a ruthenium chelate was generated by heating 2-methyl-acetophenone with 1% of a ruthenium complex in toluene. The intermediate was alkylated by an allylsilane at the less substituted carbon atom of the olefin. Similar reactions have also been accomplished with ethylene at room temperature. Benzamides do also form ruthenium chelates and can be alkylated with terminal, unactivated alkenes. Despite the electron-donating methoxy group, alkylation in this case occurred ortho to the chelating carbonyl group. The preference for alkylation at the terminal carbon atom is so high that under conditions where an internal alkene can isomerize to the thermodynamically less favored terminal alkene, high yields of linear alkyl arenes can still result, as in this example. The alkylation was catalyzed by the Wilkinson catalyst, a rhodium complex, which also catalyzes the hydrogenation of alkenes. Here, a chelating benzamide was alkylated with a silyl-enol ether, again with a rhodium catalyst. In this instance, an oxidant was required to maintain the ketone oxidation state. Aryl nickel complexes react like rhodium or ruthenium chelates. Here, transient metallation was achieved by treating the starting arene with a nickel-carbene complex and half an equivalent of sodium tert butoxide. A small amount of a branched alkyl arene was also formed. In Part 5 of this playlist, however, there is an example of the exclusive formation of a branched alkyl arene from a similar aryl nickel complex under conditions similar as those shown here. Thus, small variations of the reaction parameters can reverse the selectivity. The same strategy can be used to alkylate pyridines at position 2. Unfortunately, the quantities of catalyst and additives were quite large in this instance. 2-alkylpyridines are easier to prepare by condensation of 2-methylpyridine with aldehydes, followed by catalytic hydrogenation. In this example, a benzimidazole was alkylated with styrene and a copper catalyst. A high yield of the branched product resulted. Now, a few examples of alkylations with polyenes. Naphthalenes and quinolenes often behave like non-aromatic butadienes because only one of the two rings is truly aromatic. Here, benzene was alkylated with quinoline and an excess of strong acids. The pyridine ring remained intact, while the butadiene substructure reacted twice with benzene. From phenol and 1,3-butadienes, chromanes can be prepared, as in this example. The highest yield was achieved with tin triflate as catalyst. Allenes are particularly reactive. The starting allene of this example could be cyclized either to a bicyclic or a tricyclic structure, depending on the reaction temperature. Let's check some examples of the alkylation of arenes with electron-deficient olefins, such as acrylates, acrylonitriles, and related compounds. Such alkenes carry a partial positive charge at the terminal carbon atom. Here, treatment of dibromobenzene with dimethyl acrylic acid and an excess of aluminum chloride yielded 72% of the expected product. A similar reaction could also be catalyzed with an excess of triflic acid and required 7 hours at 45 degrees Celsius for completion. The electrophilicity of alpha-beta unsaturated acids, or esters, depends a lot on the substituents at the beta position. Most reactive are unsubstituted acrylates, while dimethyl acrylates, like the starting material of the previous example, or cinemates, are quite unreactive. Under forcing conditions, the initially formed dihydrocinamic acid was cyclized to an indenone. Thus, strong acids can convert carboxylic acids or esters into acylium cations, which can then undergo Friedel-Crafts acylations. Nitroethylenes are also electron deficient and can be further activated by protonation. Aqueous workup with strong acids or bases, however, can bring about a Neff reaction, that is, the hydrolysis of the nitro group to a ketone, as happened in this example. Cyclization to an indenone becomes easier still if, instead of an acrylic acid, some activated acrylate is used, for instance, an acyl chloride. Here, only hydrogen chloride was formed as byproduct, which did not deactivate the catalyst. Cinnamic acids are also electron-deficient olefins and can alkylate and acylate other arenes, as shown here. With a large excess of triflic acid, benzene was always acylated by the carboxyl group. The extent of alkylation and cyclization depended, however, on the para-substituent at the cinnamic acid. Here, a vinyl ketone was generated in situ from an acyl chloride and ethylene. Cyclization then gave a tetralone in high yield. Phenols are tautomers of cyclohexadienones and may react as Michael acceptors in the presence of acids. In this example, a dication was generated from cresol and aluminum chloride and then arylated with benzene. Phenols can be alkylated by electron-deficient olefins even under alkaline conditions. Here, ditert-butylphenol reacted with neat methyl acrylate and catalytic potassium hydroxide to the expected dihydrocinamate. Unsaturated aldehydes can be activated by condensation with secondary amines to intermediate iminium salts. In this example, a phenol was alkylated with cinnamic aldehyde and an excess of N-methylpiperazine. Despite the many potential products, one main chromene was formed and could be isolated in acceptable yield. The starting 4-hydroxymethylphenol is an unstable compound with a high tendency to oligomerize. This here is an example of the enantioselective alkylation of a benzamide with a succinimide. The benzamide was metallated with an enantiomerically pure rhodium catalyst and then alkylated. Similarly, nitrobenzenes can be alkylated with succinimides via intermediate rhodium chelates. The reaction conditions here were slightly acidic. Rhodium complexes can also catalyze the alkylation of pyridine N oxides with acrylates, Here, the reaction conditions were alkaline. In this example, a vinyl ketone was generated by dehydrogenation of an ethyl ketone and then used to alkylate the rhodium chelate of 2-phenylbenzoic acid. Again, as in the previous examples, a high temperature was required. Heck reactions of allylic alcohols usually yield 3 aryl propanels instead of the expected allyl alcohols because elimination of palladium gives preferentially an enol. Here, 2-chlorothiophene was alkylated directly with an allylic alcohol and catalytic palladium. The ligands prevented precipitation of metallic palladium, and the silver and copper salts reoxidized palladium-0 to palladium-2. The thermal rearrangement of allyl phenyl ethers to 2-allyl phenols, the Claisen rearrangement, is a further strategy to alkylate unsubstituted arenes with olefins. If both ortho positions are occupied, 4-allyl phenols will be formed instead. Here, the starting ether was heated to 230 degrees Celsius for 1 hour, but with catalysts, lower temperatures can be sufficient. In this example, the reaction was catalyzed by a Lewis acid and only required heating to 130 degrees Celsius for 1 day. Claisen rearrangements can also succeed with substituted allyl groups, as in this example, and an allylic inversion is usually observed, consistent with a concerted mechanism. Aryl benzyl ethers are thermally more stable than allyl ethers. Here, after 8 hours at 286 degrees Celsius, 70% of the starting material still remained, and only small amounts of benzyl phenols were formed. It has been shown that such reactions proceed by radical intermediates. A concerted reaction would cause de-aromatization of the benzyl group, what requires a lot of energy. Interestingly, even methoxyarenes can be rearranged to methylated phenols, but again, these reactions are less smooth than Claisen rearrangements. Heating azo-bis isobutyronitrile with aryl sulfoxides can yield aryl acetamides by the Claisen-type mechanism sketched here. Isobutyronitrile radicals dimerized to an electrophilic ketene imine, which acylated the sulfoxide and then added to the arene. Another exotic example is the rearrangement of N-aryl 2-vinyl azididines, which are strained allyl anilines. Depending on the catalyst and reaction conditions, either 6 or 8-membered heterocycles were formed. I've sketched here one possible mechanism for this reaction. Under the mild conditions of the first equation of the previous slide, the reaction stopped at the 8-membered ring. If the reaction was allowed to proceed, this compound fragmented to yield formaldehyde, which catalyzed further rearrangement to the final vinyl tetrahydroquinoline. Here are some more examples, also listed in the description of this video. Under the Posts tab of my channel, there is a copy of the slides. The next video of this playlist is about the alkylation of unsubstituted arenes with alcohols, aldehydes, and ketones. These reactions are important for the industrial manufacture of symmetric diaryl methanes, which are important intermediates for dyes and polymers. See you there.